Swayam Prabha. Digital India. Educated India.
So, what we do today, we will extend what we learnt yesterday and apply for a battery. Okay. Today, we are going to talk about lithium ion battery, and time is only an hour. So, I will take you through something very important, and I think this is removed in your +2 syllabus. There is something called solid state chemistry. Okay. So, this is how they will keep on reducing. After maybe 100 years, you will get to a book of 1 page only. Isn't it? All important concepts they should introduce early. I don't know who is there in the committee. Right. Now, look at this. I show you a compound. Okay. So, this compound is a crystalline compound. What it means is the position of lithium, cobalt and oxides are fixed and they will be repeating in space, so that you form a crystal. A crystal is a repetition of one particular volume, which we call it as unit cell volume, and unit cell volume will be there, which will be repeated. Like you are stacking the square box of identical sizes, then what you will do? You will repeat in some pattern. You can repeat square box the pattern you want. Suppose I have a square box, I can put it like this in the first layer, the second layer I can put it like this, correct, no? The third layer I can put it like this, right? Or I can put it like this, exactly one over other, right? There is little staggeredness here, but here just an eclipse type, okay. So, if you have a minimum volume, that volume can be repeated in some fashion in space. So, if you repeat like that, you will get a big solid. So, every solid crystalline metal you see is having some sort of repetition like that. And what is how I define the boundary of the square box? It is defined by the atoms which makes that box. So, if I make a square, it means in the corner there is something, the face there is something, right? Think that way. So, now I have a material lithium cobalt oxide and I wanted to remove lithium out of this, okay. If I remove lithium out of this, then when I write LiCO2, it is not one molecule of LiCO2, and second thing, it is a crystalline compound and which is in the space. It means it is no one molecule like methane, CH4, one isolated methane you can take it out. Acetone, CH3CO, CH3, one isolated acetone, because between the two acetone molecules there is only a weak force like van der Waals force. Whereas in extended solids like this, in all direction the bonds will look identical. So, there is nothing like one LiCO2 you can take it out. If you are taking it out, you have to take some few Avogadro numbers of them, that is how it will come. Because it is not like a molecule like methane, ethane, carbon dioxide, wherein one molecule is clearly distinct from other molecule because they are connected by the van der Waals force. So, you can just remove them, but here it is not that. LiCO2, the cobalt and oxide and lithium and oxygen are connected by the ionic bond and is extending in all direction. Therefore, you cannot say which is a molecule here. You can call it as a formula unit. What is formula unit? You take something and estimate how much lithium is there, how much cobalt is there, how much oxygen is there, and divide by a common number, and it will reduce to LiCO2. So, that is a formula unit, right. So, this is an extended solid. Now, I am trying to remove lithium out of this because I have Avogadro number of them, a few of them I can take it out. So, I take it out and x is a fraction here, x is less than 1, okay. So, if I take a fraction x from there, so I am taking out lithium ion, then this lattice will now gain a negative charge, correct, because I am taking out a cation, but I wanted to keep it as a neutral. That means I have to also take out simultaneously electrons. If I take x lithium ion outside, how many electrons I should take out to maintain electron neutrality? X electron. Where that x electron will come from? Because lithium is already lithium ion. It can come from oxygen or it can come from cobalt because it's a transition element, okay. So, the cobalt is in a 3+ oxidation state here, now we will go to 4+ oxidation state. Okay. So, you see as you remove lithium, okay, so you are going to have x lithium taken off and along with the x electron taken off, and you see the cobalt, sum of the cobalt proportional stoichiometrically to the amount of lithium removed gone to the higher oxidation state. So, what is a redox couple here? It is a cobalt 3 plus 4 plus is the redox couple here, because the reverse reaction make the 4 plus to 3 plus again. So, the redox couple here is 3 plus 4 plus, but in electrochemical series you might have seen there is a potential given for these 3 plus 4 plus redox couple, the electrochemical series. But remember, I told you the potential also depends on the environment in which it is there. Why? Yesterday we discussed crystal field theory, wherein when you put it in a ligand environment, the way the d orbitals face repulsion because of the electrons in the ligand, it will be going to be different, because some of the ligands may be very strong, they will come and really repel. So, the splitting will be even more, d orbitals may split even better. Some of the ligands may be very weak, when they come near they barely split. As a result, the energy level of your d orbitals for even the same ion going to be different. It is a function of our ligand. Okay. So, now we have put it in a ligand which is oxide here. So, you have put it in a sea of oxide ion. So, oxide ions now going to interact with your cobalt ion. So, cobalt 3d orbital now will split. Okay. Cobalt 3 plus d. What is number of electron in cobalt 3 plus d? How many electrons are there? 4 electrons. D orbital, how many electrons is there in cobalt? 3 plus. I don't know. I have no idea. You know, at least up to 3D series you should mug it up. Okay. You find it out, it will be 3D 6. Okay. 6 electrons will be there. So, when you remove 1 electron from there, because this is going to have a 3d6, that means you will have a T2g Eg, T2g set of orbital Eg. What is Eg set of orbital? D x squared y squared, d z squared, or these are axial orbitals. These are all interaxial orbitals. Okay. So, it will split like this, otherwise the d orbital would have been like this, but now it has got split because of the ligand environment here. So, the 6 electrons will now go here, because this splitting is so high that energy is more than the pairing energy. Therefore, electron will only forced to pair here. Okay. And then if you now oxidize taking a lithium out, then 1 electron from here will go out. Okay. So, that is how you look at it. Or as you said, alternatively this oxide can give electron become peroxide, and that is one of the problem in this material, because the oxide energy level 2p oxide energy level is almost similar to T2g level. Therefore, when you try to remove electron, there is a chance electron can come from the oxide also, but that is all outside of scope of discussion of today's class. Today just assume it is coming from the transition metal ion. If it comes, then you have this fellow. Okay. Now, this is called de-intercalation. Why it is called de-intercalation? Because lithium is in a specific site, from that site we have removed this lithium. So, it is called intercalation, means putting it in the void. De-intercalation means removing it from the void. So, it is a de-intercalation process which I have written here, de-intercalation. Okay. Now, let us halt discussion on this and we will go to what we know. What is the intercalation? Means put it in the defined void. De-intercalation means take out from that void. Now, I have taken the lithium out of the void, therefore, it is called de-intercalation. Now, we will discuss what is void. Okay. So, now all of you must be knowing sodium chloride structure. I do not know whether that also removed from the paper, I do not know. Okay. So, how do you define sodium chloride structure?
Around every Na plus there are 6.
Okay. You are describing as if it is a molecule. There is a sodium ion, around that there are 6 chloride. So, NaCl6 is the formula, is it?
No, sir. Around every Cl minus is also.
So, it is an extended solid.
Yeah.
So, it is an extended solid. So, that is not a good way of defining then. Let us now look at it. That sodium chloride crystallizes in something called cubic close packing. Okay, what is making the close packing? It is an anion generally makes, because anion is generally bigger than the cation. So, you make a structure with anions, obviously you will have some voids left out in that structure, there you put it your cation, okay. So, that is how you look at it. Now, you see here I have this fellow chloride ion which is making the lattice. This lattice is called triangular lattice. If you see any 3 you connect and see, it forms a triangle, okay. Any 3 you connect and see, it forms a triangle. So, it is a triangular lattice. So, a triangular lattice 2D lattice of chloride ion. On top of that I will put another triangular 2D lattice of chloride ion which is yellow in color, but I am not putting exactly the over the previous layer, there is an offset, okay. So, it is put at the junction of 3 particle, okay. This is put at the junction of 3 particle. Now, I can again put one more layer. For this third layer I have 2 options. I can put either above this red one or I can put again at the junction of 6 particle. It is not junction of 6 particle, it is again junction of 3 particle, because this particle is in the top layer, these 3 is in the bottom layer, but you can from 2D you can look at as if it is a 6. So, when I say 6, it is not correct, because that means I am putting in between these 2 layers, then only all the 6 will be in connection, but I am not doing that. I am putting above this yellow layer. So, strictly speaking it is only 3, but the void, if you look at it, is as if there are 6 of them making that void. So, above this 6 coordinated void, I am putting the third layer. So, I put layer here, 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 right. So, like that I have gotten a 3 layers. Since these 3 layers are distinct from each other in terms of its position coordinates in space, we call the first layer as A layer, second layer as a B layer, third layer as a C layer, okay. And then fourth layer will be like A layer. So, it means I am going to follow a pattern A, B, C, A, B, C, ISA, okay. Like they will be going on doing, and then so that is why I put it in 3 colors here, and I have connected the atoms in such a way that you can appreciate there is a face centered cubic lattice is forming. What is a face centered cubic lattice? You have atoms in the corner, you have atoms in the face. There are 6 faces, so there are atoms, 6 atoms right in the face of a cube, and there are 8 atoms right in the corner of the cube. So, since I told you this lattice is repeating in the space indefinitely. So, if that is the case, the atoms in the corner will be touching with how many unit cell, because whatever I have drawn is a unit cell. A small box which I have drawn is a unit cell, because that unit cell if you repeat, it will expand in the space, okay. So, the atom in the corner is actually common to multiple unit cells. How many unit cell will be sharing that corner atom? 8. So, the contribution of this corner atom to that particular unit cell is only 1/8. There are 8 of them, therefore, 1 atom comes out of the corner atoms to that particular unit cell. How many atoms are in the face center? 6. How many unit cells share one face? So, 6 into 1 by 2 is 3. That means that particular unit cell can climb only 4 atoms to it, correct no? So, it is called face centered cubic lattice or cubic close packing, CCP. So, in CCP the definition is you have a CCP packing, that means you have atoms in the corners and face, okay, and there are 4 atoms belong to one unit cell, okay. Now, what happens you have to see, look at these atoms in the face center, and I minimize the size of the corner atoms so that you can appreciate a polyhedra that I am going to bring out. If you connect these 4 atoms, you will get a square, and if I connect these atoms to the apex atoms, you will get a closed object called octahedron, right, octahedron. So, how it will look like? Right, you get an octahedron, and in the center of the octahedron what is there? Nothing is there, that is called void. Now, we are going to utilize that void to put something there, cation. If in case this lattice is made of anion, then we will throw cation there. If in case this lattice is made of cation, we will throw anion there, okay. Now, again what I am going to do, I minimize the sizes of other atoms except these 3 face atoms, 1 corner atom. Now, if you connect these 3 atoms, you get a triangle. Connect this to the apex atom, you get a pyramid. So, it is a tetrahedron. Why tetra? There are 4 triangular faces which makes this closed object, that is why it is called tetrahedron. Why octahedron? There are 8 triangular faces come together make a closed object called octahedron. okay, but octahedron is only 6 atoms, but 8 faces. Now, if you carefully look at it, these 3 atoms over here are the same 3 atoms over here. That means an octahedra and tetrahedra are sharing the face. Okay. So, an octahedra which is sharing a face with a tetrahedra. How many tetrahedras are possible? 8, because there are 8 corners. So, in 8 different direction there will be 8 tetrahedra. How many octahedra is possible? 4. Where are the remaining 3 coming from? You see, one comes from the body center. Body center means this is the center of the body. Other comes from the edge center. But I have to borrow 2 atoms from the neighboring unit cell in order to visualize the octahedron. Correct, no? Appreciate?
Since it will be shared by 4 atoms, then net only.
Net is 4.
Effective will become.
Effective is 4 holes, 4 voids. Okay? Because you see, how many edge centers are there? There are 12 edge centers.
And each is shared by 4 atoms.
Yes, 4 neighboring unit cell. Therefore, 1 by 4 it becomes 3. Already 1 you got from the body center. Right now? Clear? Any question on that? So, we have 4 octahedral voids belong to this unit cell, and earlier we calculated 4 atoms belong to this unit cell. Now, we calculated 4 octahedral voids belong to this unit cell. Also, from the figure we can understand there are 8 tetrahedral voids belong to this unit cell. So, I am going to generalize. If I have n atoms, n octahedral voids will form and 2n tetrahedral voids will form. Because I told 4 atoms belong to this unit cell, that forms 4 octahedral voids and 8 tetrahedral voids. So, if that is the case, then I can generalize saying if I have n atoms, I will have n octahedral voids and 2n tetrahedral voids. Correct, no? Makes sense? Is it clear?
So, but this is only for face center.
Yes. Right? Now comes the interesting aspect. Since the number of atoms that forms unit cell and number of octahedral voids are same, if I ask you to imagine this CCP lattice is now made of chloride ions and all the octahedral voids I will plug in with the sodium ions, then what would be the formula? NaCl, because n atoms, n octahedral voids. Now, if I am saying you throw sodium ions in the octahedral voids, you might have thrown n sodium ions for n chloride ions. Therefore, the formula is NaCl. So, what is the structure of NaCl now? It is a CCP array of chloride ions holding sodium ions in the octahedral voids. Do not say there is one sodium ion around there is 6 chloride ions. That is looks like a molecule. It is not a molecule, right? Correct, no? So, when I say lattice, it is understood it is infinite. So, we have a CCP array of chloride ions. In that, sodium ions are put in the octahedral voids, all the octahedral voids. Okay. So, that forms a NaCl. Now, let us look at this. I have 2 NaCl and I will write it as Na2Cl2. I am going to do some substitution to draw analogy. One sodium atom I am going to replace with the lithium atom. The second sodium atom I am going to replace with the cobalt. Both the chloride atom I am replacing with the oxide. Then you get structure of LiCO2. So, how do you define the structure of LiCO2 now? It is a CCP array of oxide ions in which alternatively. Okay. Therefore, you have a layer of lithium, layer of cobalt, layer of lithium, layer of cobalt. Why do they segregate like that? They could have gone randomly also. Because of the size difference, they themselves segregate when it crystallizes, because that is the most thermodynamically stable state. So, automatically forms, that is good for us. So, you have a layer of sodium ion, layer of lithium ion, layer of cobalt ion. So, that is the structure of this. But the unit cell cannot be cubic. Why? Because you have got 2 cations. So, if you try to find out the minimum volume in which you will get all of them in the ratio 1:1:2, it will become a rhombus. lattice is same, unit cell is different. Not tetrahedra, rhombus, R. LiCO2, that be in the ratio of 1:1:2. It will come, it will come. Okay, right now, any question?
So oxygen is placed in the octet.
No, oxygen, you can say, if I say lithium and cobalt are making CCP lattice, then you can say oxygen is placed in the octahedral void. But by definition we use to form the lattice we use anion, because that is generally bigger compared to cation, therefore we use them. So, right way of saying is oxide ion is at the corner and the face center of the cubic lattice, right now. So, otherwise in one word if you want to say, it is a CCP array. Which is octahedral shape? LiCO2 is not octahedral shape, it is a rhombus, you will see now, right. Rhombus in 3D, planar means what? Then we have only like a sheet, but it is a 3D material, okay. So, you will have like this, right, something like that, a tilted square, cube, yeah, just shift it like that, elongated in the corner, opposite corner. LIS?
Can you like represent LiCO and O2 in that diagram?
It will come, it will come, it will come.
Okay.
Yeah. Then, any other question?
So can we have similar lattice structure in which the first cube has the fluoride ions at each face and then the second one has. So can we have a structure where the So can we have a crystalline structure where the first one has a fluoride at the center of each face and the next adjacent unit has a chloride, but the cation is the same or has the same positive charge?
Theoretically yes, but you have to make it.
So has it been manufactured yet somewhere?
Not easy what you are saying. We call it as anion doping. You have first one anion and then selectively some anions you dope with another anion. What you are asking is what we have already done. For example, imagine I had sodium chloride. What I have done here, if I would have had the same element here, it should have been either CO2 or it should have been like a Li2O2, correct? But Li I removed and put a cobalt there, correct? No. So, you can see clearly already I have two cations which are alternating in some fashion. Similarly, you are asking for anions, it may be possible, okay, but you have to see, because finally it has to be electron neutral. You cannot simply take one element, plug it with another element, you should know its oxidation state, size and all that matters.
So in that case the unit cell would not be defined like that. If each succeeding.
Every time you do some changes, then you have to again define a minimum volume which repeats in the space.
Yes, sir.
And you have to look at the shape of that minimum volume.
Yes.
Whatever the shape, that is a unit cell. If it is a rhombus, rhombus. If it is a tetragonal, tetragonal. If it is orthorhombic, orthorhombic. Correct?
Yes.
So, what was a cubic, the moment I add one extra cation, it is no longer cubic. It has changed its shape. Based on that only we are saying it is no longer cubic, it has gone to rhombus. It is not a face center. But the lattice is still the same. It is a CCP lattice of anion. Just because we have a definition for the unit cell, by that definition, if you look at it, the minimum volume has a different shape than what NaCl had. Therefore, we are calling it like that.
So thank you.
Yeah.
Sir,
Hmm.
so is it like if I give a ionic compound, can I like predict what sort of a shape? Now, as you said, you put lithium, cobalt, and oxygen, it became like a rhombus three-dimensionally. So, how if you give a random compound, how do we know which shape?
There are some guidelines based on the experience. Okay, there are something called there is something called radius ratio rule. If everything is possible theoretically, by now we would have reached everything best. the best material for this application, best material for that application, because you know everything how to predict theoretically. But unfortunately not.
How did
Okay.
we predict this one?
No, there are something called, by experience, people have worked out something called radius ratio rule. They use that to say whether or not some substitution is possible, and then based on that they may make some guesses. Okay, so it is only a something you will get to know. There are some guidelines are already there in solid state chemistry. You can use that, number one, so that you can make some guess, but no guarantee that you will get that compound. That comes by experience only. Okay.
So,
Hmm.
so is that radius ratio rule because every corner, like in this FCC, every corner atom should be in contact with the adjacent faces, like face centers, and if
You are talking about hard sphere model.
right,
Okay, not necessary, right? You can have open space in the lattice.
but will it still be called an FCC cubic lattice?
Yeah, it is still FCC. Why it is not FCC? Because if you connect to those atoms, you are finding one atom in the middle of the face. So, it is still an FCC. We are expecting that to be connecting and all that thing, but again this radius is something variable. How we define now radius? The midpoint of these two, then automatically you are including that space also along with the ion. And when, since ions are spaced at this kind of a distance, it means why it is placed at this distance, because this is where the force is balanced. That means each other is seeing the other ion and then trying to position itself. That means the midpoint is the radius of this guy, from the midpoint to here, center of this atom is the radius of the other guy. So, the radius vary, correct? No, you cannot define one radius and then say that radius is preserved in your lattice, no. And again, if you look at it, if you put an ion in a water, its radius is different now. Why? You need to look at the water of hydration, I mean the hydration, solvation, and then you define a size for the ion, correct? No. So, it is not one single answer for radius. I can say the ion can have infinite radius also, if it has influence up to the distance, right?
So you said like for generally in this the anions occupy
Make the lattice.
make the lattice. So for example in compounds like cesium chloride, their cesium is much bigger than chlorine. So will cesium make the lattice or will chlorine still make the lattice?
Compound does not know which is lattice, which is void. It is for our understanding, we call something as lattice, something as void. You can also define the structure in terms of cesium and put the chloride in the voids. Who stopped you to do that? It is all only definition. So that conveniently we can visualize what I am trying to say. If I have two definitions, I will choose the one which is easy to convince you. If I take the harder one, then I will be keep on spending time with you, you will take time to understand what it is. So, these are all just a way of communicating effectively what it is. But the compound does not know there is something called lattice, there is something called void. You mix cesium and chloride without knowing all these things, it will form a structure it is used to form. It will not change day by day. Cesium, one day I will be wearing this dress, next day I will wear different dress. No, correct? No. So, do not get confused. You can define the way you want, as long as that is precise and acceptable is okay. Not necessary you have to follow what I said that you define like this only. That is a definition, because if you define that way, it is easy, because everybody is familiar with that, immediately they will grade you. Otherwise, they have to think what you are saying. If they are able to get what you are trying to say, you will get to mark. If they are not able to get, you will not get to mark, or probably your paper is kept on hold, correct?
Are these just theoretical assumptions, or can we actually? Are these just theoretical assumptions? Like, okay, this molecule will look like this, or is there any method we can use to actually say that this molecule will look like this, like the electron microscopes or anything like that?
Yeah, you can see the electron contour map, where and all electron goes, like your Google map, you turn the map, you come back and check, past 1 week, where and all you went it will have, it tracks you, correct? So, similarly we can track where and all electron is there in the lattice. So, then you make a contour map of where electron went, and then you will get a shape evolving out of it.
Is it possible to write this exact structure just from that contour?
See, for example, if I am using X-ray diffraction to do that. X-ray diffraction, something related to the X-rays interacting with the electrons of the atom, there will be a resonance between them, and then you have a diffraction, and from that information we reconstruct them positions of these electrons, and then we get a structure evolving. But you will not be able to do it for say hydrogen. Okay. Why? Because hydrogen has only one electron, so its scattering power is so low, your signal is so poor, so that you are missing that point. Imagine you are forming a solid methane. The solid methane, you know positions of the carbon for sure. Position of the hydrogen, you will put yourself, because you know it is sp3 hybridized. Therefore, if these are the positions of the carbon and these will be the positions of the hydrogen. So, you will get something directly, something by your intuition you will add and then present a final structure. So, answer to your question is, if it is a heavy atom, it is easy. It is a lighter atom, it is difficult.
So one question, sir. Sir, we just now learned about tetrahedral void, octahedral void, sir. So can there also be higher voids?
You can have. There are voids which shape what to say, I don't know. That kind of shapes also there.
Like what, sir?
Yeah, it can have 10 coordination, it can have 12 coordination, then what you call them? Yeah.
Like, sir, can there be things like higher planes of symmetry like dodecahedral void?
That's what I am telling. How many are there that spaces are there?
12, 20.
Yes, you can have. So, you can have a void of that shape, that you can put your atom.
Yes, sir.
Right
Any
now.
examples, sir?
Example right now I don't have. There are some Nasicon structure, NaSiCon. If I remember correctly, Na2, V2, PO4 thrice. Okay, there is a void for sodium also. Okay. So, these guys will have sodium in two different environment. I think these two sodiums will be in octahedral coordination, and this particular sodium will have some higher coordination, maybe 8 or 8 I think, I do not remember this one. So, if you add this sodium Na3V2PO4, this is actually called Nasicon, sodium ion superconducting material something, Nasicon. Okay. Na. Okay. This is a material used in batteries. This is NVP, sodium vanadium phosphate. So, if I do something similar to that, I think if I am correct, it is Na3 zirconium 2 PO4 thrice, then this material will be acting as a very good ion conductors. So, this is solid state electrolyte. This is solid state electrode like LiCO2 for sodium ion battery. Okay. So, you can have there, you will find some higher coordination, but you just go search in the textbooks, you might find more, but I do not remember off the head the coordination number, although I remember compound name, that number I have to look at the structure and say.
Sir, can you please repeat what's the meaning of coordination, sir?
How many coordination? How to with simultaneously with how many ligands that particular ion is in touch?
Yes.
Correct, no?
Yes, sir.
That's coordination.
Thank you, sir.
So now that compound which you have given there, now this PO4 thrice is a different entity when you see as a whole. So will it be like a different structure with then connecting to the Na2 and V2, or it will be like together as layer?
See, you can visualize them. As I said, the atoms don't know there is a polyhedra. Correct? Atoms are arranged somewhere in the space. But if you connect the P and the O4, it will actually come out a polyhedra called tetrahedra, wherein the phosphorus is in the middle of not exactly middle, the barycenter will be close to the base. So, it will be close to the base, and there are 3 base O atoms and 1 apex O atom. So, PO4 3 minus will form a what? And a tetrahedra, and this vanadium oxygen will form a octahedra. And the sodium also, 2 sodiums will form octahedra. The 1 sodium will have some higher coordination, I think 8 coordination, I do not remember correctly. So, now you see each one forms a different types of polyhedra. Now, forget about atoms for a minute, you only have polyhedras and start arranging them such that it is stable, then you get a structure.
So it's not together, as you said, separate and then comes to here or something. After
it is together.
Oh.
It is together, but the point is where there is a phosphorus, around that you will find 4 oxygen. Where there is vanadium, you will find around that 6 oxygen. Okay. Where there is a sodium, 1 sodium, 2 sodiums will have 6 oxygen, 1 sodium will have 8 oxygen around it. So, but this will be keep repeating. You will not see in the material a portion full of only PO4, a portion full of only NaO6, a portion full of only VO6. That way you will not find. These polyhedras will be mixed. Imagine all polyhedras are mixed together. Imagine the gems chocolate is there. Imagine the gems chocolate, you make it in whatever the shape you want, square, rectangle, triangle and all, and then mix them. And you will see everywhere everything, right? That is how it will look. But there it may be amorphous, because every unit volume may not have the same number of square, rectangle, circle and all. Imagine it is there, such a mixing we make it, nice mixing, then you will, something similar to that you will see, right now. But of course you have to worry about the angle at which these polyhedras connected and all, it should be same everywhere when you.
Sir, you said in that Nasikon, the 2 sodiums will have different coordinations. Given that they have 2 different coordinations, do they behave differently?
Yes, they behave differently. That's why it's called superion conductor.
How do they differ?
You guys are asking questions which PhD students must be worried about. Okay, how they are different? See, let's look at this way. This is a famous example I used to give. Some 10-15 years ago, if you have played video games, there will be one mountain keep coming, and the one guy will be going on car. The car will climb the mountain, then drop down. Then there will be some fuel you collect, continue. But if you unnecessarily brake or accelerate, you may lose energy, then you will not go to the end point. Correct, no? If you look at carefully there, it will go up, then without using fuel, it can climb down because of gravity, right? Imagine I have a situation like this. Okay, which one you think easy to climb and without losing much energy, or you given fuel is effectively utilized and go to the end point, which one is?
Second one.
Second one is easier. First one, you go up, lot of resistance, you go up there, then you get your, what do you call that, momentum because of gravity, you come down, but there are frictions. So, energy you gained here is actually less than what is required to reach here. So, with that energy you may go up to here and you will be rolling back.
But the second one, I can say that since the shorter one is like half the height of the taller one, then it can effectively only reach just a little lower than the half. But we still have this.
See, the point is periodically you are getting some gas. That game, it is not the game without giving any energy. Initially you are given some energy, periodically also you are given some energy. All you need to do is you have to effectively utilize that energy. That energy is given to you to use that energy to the friction, whatever it is you are having, to compensate further, it is given. So, you have to effectively use it and keep going. So, you have to also think in terms of the driver's point of view, how easy it is. Theoretically, yes, probably some of them works out to be by energy conservation principle, it is possible. But here when you do this action, one form of energy is continuously converted to another form of energy and back and forth, and one process is efficient whereas the other process is not efficient. For example, you can convert everything into heat easily. Converting heat back to some other form of work is not always efficient. All that if you put together, practically this is easier, that is tougher to do. Correct, no? So, in order to continue your journey, they are giving fuel periodically some interval, maybe some calculation. So, you have to play such that you do not accelerate too much or you do not decelerate so much that you lose, and decelerate means you are releasing energy in the form of heat. That energy is not available back to you. Once you make a heat out of your journey, that heat is not coming back and becoming petrol for you again, no, correct. So, all problem is there, but why I brought up that here, the discussion is different, because you have sodium in 2 different forms. Imagine one sodium is lying here, one sodium is lying here, these two are very different sodium, because this fellow is at this energy, this fellow is at this energy. Now we are trying to move the sodium through the lattice. So this fellow will climb, or say this fellow may not be here, say somewhere here. Okay. So this fellow is climbing. So at the same time, say this fellow is descending. Imagine between them there is some bonding. Bonding means invisible. There is some exchange of energy. Okay, such that when this fellow is trying to climb, he borrows the energy from him because he generated some energy by going down. So that energy is given to this guy. In other words, there is some sort of resonance between them. Okay. So the net energy I have to give for this process in the form of over potential is reduced. Whereas here the over potential I have to spend for moving the sodium ion will be higher. Whereas here, since there is a synergy between these two guys, instead of allowing the energy to escape as heat, that energy is exchanged between these two guys, and therefore they are coordinately moving, taking less energy from me. Still you have to give energy because you are moving, essentially relocating sodium ions from one side to the other side. Obviously you have to spend the energy, but how much you spend is the question. Now you are asking these two guys internally exchange energy, remaining I will give. Whereas in the previous case there is no such thing, because all sodium ions either moving up, all sodium ions were either moving down. Always you give energy. When it moves down, you ask them to give back the energy, they will give back obviously in the form of heat, which I cannot supply back to the system. I have to again supply in the form of electrical energy. So every time I have more loss in that process. Whereas in the second one, the amount of energy you have to spend for the same movement of same number of sodium ion movement for the same distance is less. Okay. So this kind of cooperative motion will be there between the ions that make the ion move faster. That is why it is called super ion conduct. Otherwise it is called ion conduct. When I say super, there should be something super, right? What makes it super? This kind of coordination is there. This is one model people have proposed. There are several models like that, how this particular material has more conductivity than any other material. There are some logics, people look at some theoretical calculation, understand there are new pathways by which this is moving, that is why this is energy is lower, things like that. Okay. So these are all something is a research topic, even it is puzzling for us how it is happening. Then we do some detailed calculations, detailed analysis, and then propose an hypothesis. This is probably the most probably what is happening in the material. See, measuring property is easy. How much is temperature? You can measure. Why the temperature there? We cannot say that until unless we know what we are doing. Suddenly, suppose this floor heats up, I can say definitely floor is heating up. Why it is heating up? I don't know. Is there any electrical line going underneath which is faulty, or is someone literally heating from the bottom? What is happening? Or some lava is going to emerge? I don't know. For that, I have to dissect this and understand what is going on. That is a research. But property measurement anyone can do. I can say it is heating up. Yes, from the heat, I measure the temperature and tell you. I can also tell you how much heat is coming out. Do a calorimetric measurement, I can tell you. But why is the question we have to answer. Right now? Any other question?
Sir, the same thing as the second thing. So, and as for the second one, what was done with those two sodium ions? Isn't it applicable for the first one?
First one has only one kind of sodium ion, no? They are all in the same trap. Here these two guys are in different coordination, means they are in different energy. So one probably moving up, other one probably coming down, or depending upon how they are placed, right?
Here also they could be placed, right?
You can't, because they are identical. See, the crystal lattice, the beauty you should understand, they are repeating means they are identical. You can't put one sodium in octahedral void, another sodium put it in the tetrahedral void, you cannot do that. As long as it is in the same octahedral void, they all have the same energy. So you can have to follow, right?
Would this variable coordination thing be easier for lithium because, or I'm not sure which one, but it also has a more efficient with 12 coordination number packing, like NCP or something. I'm not sure, but
No. Okay. The problem is you need to have the material in hand to understand that. You can have also with lithium, there are some materials called lesica. Okay. But specifics of those things you have to go back and look at what is the material, where the lithium is present, what is its coordination, all that you have to look at it. Generally, if the void is bigger, it is easier to move. So, generally, if easier to means what, conductivity must be better. Conductivity must be better means if you use that material as an electrode material, it can charge, discharge at high current. So, that means you can charge, discharge your battery quickly. But you are able to charge, recharge battery quickly, but your unit cell volume is bigger than the usual unit cell volume. What it means is your battery also will be bigger. That you don't want, right? No. So, if you want things to be compact, but things has to move faster. It's like you are asking, I want my street will be like Ranganathan street during Diwali, yet I have to move at the speed of 100 km. This is a tough thing, and that's what you guys are asking for your EV car, right? So, it needs a lot of research to do that. Unless everybody in that crowd is programmed so that even though it is crowded, without colliding we can move. If everyone is independent, then we don't know who is colliding with whom. It's all randomly moving. That there will be a huge collision than order. Huh?
So you said that sodium zirconium phosphate is a solid electrolyte. Could you please explain the working of a solid electrolyte as opposed to an aqueous medium?
It's all same. In aqueous medium also ion is moving, solid electrolytes ion is moving in a solid matrix. Correct, no? See, rest of them are fixed. In aqueous medium, what will happen? Your other ions in the solution or other solvent molecule in the solution also can displace as you move. It's like you are moving in a kind of water or something. As you move in the water, not only you move, you are also displacing water. Whereas in solid matrix, those waters around you or the other ions or solvent around you are more or less fixed. So, oxidant position is fixed, vanadium position is fixed, phosphorus position is fixed. You are just moving in the gap between them, right? But when you move, sometimes they may dilate a bit, because locally when you approach close to phosphorus, approach close to vanadium, there will be a local interaction. As a result, they may give you some way, okay, you go now. Once they go, they come back to the original place. So, some sort of breathing will be there as you move. But in the solution case, that breathing will be more, because when you go, that water will just go like this too far compared to the solid case, right. So, only that is the difference, the amount of breathing that happens. But overall you will not see any volume changes, because when you are entering, similar time some ion is exiting. So, there is a volume contraction there is a volume expansion here. Overall there is no net change. You take water, sodium ion is keep moving, do you see water going up and down? No. That means somewhere there is a contraction, there is an expansion, so net effect is cancelled. But locally if you look at it, yes, you will see some displacements. Right. Any other question? So, now what we do, we will complete the discussion on battery.
Swayam Prabha, Digital India, Educated India.